Greetings, students. Mr. here with you again today. 12-2 semester. Equilibrium. We have to talk about 3 different cases. You'll see involving solutions. We have or gas. With which involves gas. These are gas reactions. We talk about KSE, which is solubility or reaction there. In particular, is how soluble or a particular substance is in water. Value as we explained in our lab. Substances. Move along. Talk about a little and revisit the value of the Q and relationship equal to kind of showing the normal we would have been 7. If you're in honors chem, in a few days after that. But again, we are not referring to these, should be referring to be modified due now located on my campus. Freeze here. Letting up. Okay. And there they are. Again, value of K and its relationship, the reaction quotient. Recall of K, or how large or small it is the extent to which a reaction proceeds is large. Remember, K in general, regardless of what type it is an expression of concentrations over reactant concentrations or pressure. It's large. If this value is large, the reaction tends to proceed to the right. Is it equal? And what that's saying is since this number up here must be a bit larger than the number here, which means we must have more equilibrium than we do. So the reaction tends to proceed to the right or favor the products. If K is small, then just the opposite is true. The reaction and the mixture will continue with reactant. So if it's small, mathematically, that means that this number down here has got to be larger than this number up here. At equilibrium, we have mostly reactants, or the reaction favors side. Recall to calculate the concentrations of reactants and products, more pressures, once equilibrium is used. Remember an ice chart, and we've talked about charts several times in several different lessons. We're going to revisit ice charts here again. In addition, K allows one the ability to predict the direction in which a reaction mixture will proceed from initial conditions to equilibrium. Suppose that we have this reaction here, the solution of ammonia, nitrogen, and hydrogen. Have this in an enclosed container. Equilibrium going on the forward and the reverse reaction. So that we put in 2 molar concentration of hydrogen, 1 molar concentration of N2, and molar concentration of NH3. Now, we have talked about it in G when we our reactants in the container and then seal the container, our concentration or pressure of our products is zero. However, that does not mean that it has to be zero. There's no law saying you cannot introduce some product into the container initially. All right, that is entirely feasible, and of course, we do that is check the equilibrium concentrations or pressures of all the substances. Initial concentrations. So these are initial concentrations in K expression. All right. So K for this reaction, again, crossover reactants, will be the concentration of NH3, our product, squared over the times the concentration of H2. If we plug initial numbers in the K expression, we get a value of to 3 sig figs of 0.500 or 5.00 times 10 to the minus 1. So let's move this up a little bit. 1. So this initial concentrations were put in the K expression, we get this value C. According to an example that we did, we have this same reaction at this same temperature, 472 Celsius. Kc for this reaction at equilibrium 1.04 times 10 to the minus 1. So this K, we're still calling it, actually isn't. So this was initially, and this was equilibrium. Take a look at those two numbers, all right? So if we initial concentrations, get this value for A. If we use equilibrium at that same temperature, we get this value K. Again, look and see how those two compare. Over here is larger than this one. So as you go from initial to equilibrium conditions, the value of this ratio of product reactants is decreasing in value. All right, it is decreasing. Thus, the only way that can happen for this number here to get smaller, the only way that can happen is if our product concentrations our reactant concentrations get larger and our product concentration, in this case NH3, gets smaller. For this number, again, for this number to get smaller, then this number has to be larger, and this number has to be smaller. All right. Thus, start on the next chapter now. Thus, the reaction proceeds towards equilibrium with the formation of hydrogen and hydrogen, and thus products. And the reaction is being right to left. In other words, this reaction is to the forward reaction. Since is getting, if in product concentration into a expression rather than the RF, then constant is now not called an equilibrium constant. It is now called a reaction quotient or Q. We talked about Q briefly in Unit 11. Unit 12.1, I believe, when we talked about the fact when we get conditions from conditions, which are 1 mole we needed that ratio of Q. That unit, but now here we're kind of focusing a little bit more on that. So a couple things up. Okay, in regards to Q. Q and K value only in equilibrium. Remember, Q and K, same ratio of products to reactants. Right? The Q is where these concentrations are what they are, and K is what those equal value, I should say. If Q is larger K, as in our example we just did, reaction approach equilibrium. Right? The value is smaller. Larger than K, then at equilibrium, that number has gotten smaller. All right, as equilibrium is achieved. And then on the other hand, Q is less than K. Right? If Q is less than K, then initially this value is value to get larger as equilibrium is approached. Then now the opposite is true. The product concentrations must be getting larger. The and so that value is going to increase. All right. So now the value gets larger as equilibrium is achieved. Okay. So there's three things we need to know in regards to the comparison of Q to K. Fine. Q and K are both solved the same way, the same ratio of products to reactants. The K is Q is determined with initial values. Okay. All right. So let's look at here and then let's take a quick look here at something. There it is. Yes, that's what I was looking at. Okay, so got to double check what I'm doing. Okay. So in the reaction from example 4, which we did a few days back, whereby Kc, this reaction right here was 50.5. That's how the reaction will proceed to reach equilibrium. All right. At 440 Celsius, this is the same conditions that we solved that Kc value. If we get with 0.0200 molar of HI, 0.0100 molar of H2, and 0.0300 of I, this would be it. All right. So here was our reaction from example. We're running the same reaction at the same temperature. We have a value of Kc. We're not going to determine with these initial values what the value of this Q. So Q again is the same way as K is over reaction. So this is HI squared over the concentration of H2 times the concentration. And so if we throw the numbers in there, we're going up here. HI was 0.02 squared. Hydrogen, right? 0.0100. And nitrogen then, or I'm sorry, nitrogen, but iodine was 0.0300. And go. So if we do that, making sure we don't forget that, about these two here, to the three things, we get a value for Q of 1.33. All right. Remembering then that Kc for this reaction reaction was 50.5. Same. The ratio of products to reactants was this value. At equilibrium, that same ratio of products to reactants is 50.5, which is much, much larger. All right. So what can we say about that? Well, since Q is less than P, all right, then Q is increasing. That's the key point here. Its value is increasing, which is equilibrium. All right. What does that mean? If its value is getting larger, again, remembering that ratio of products over reactants. All right. Well, then it means then more products are formed as equilibrium is achieved. All right. And the reaction shifts to the right. Which is a product side of the reaction. Okay. If U is less A, then that means that ratio of reactants as equilibrium is achieved is meaning more products are formed. The reaction is favoring the right side, and so as you go from initial to equilibrium conditions, that reaction is shifting to the right to make more products. Okay. All right. So that is our lesson today. It's our first lesson for today. And this then would correspond to your assignment title Equilibrium number 6, versus 7. So now you should be able to do that. It's short. I don't think it will take you long at all. So today we're talking about what the value case in regard to how small it is, it's to Q. So, have that down. So that is the end of today's lesson. So until next time, safe, keep working. We're getting close to the end now, so keep going. And hope to see you again soon. Take care.